The number of people in line for a roller coaster throughout the day can be modeled by a function. Move through the slides to see how to use the key features to sketch a graph of a function. Then interpret the key features if X represents the time in hours since the ride opened at 10 a.m. and Y represents the number of people in line. Here are our key features. We're positive between X equals negative 0.5 and X equals 12. We're negative for X less than negative 0.5 and X greater than 12. We're increasing from X less than 1.4 and between X equals 5.3 and X equals 9.9. We're decreasing for between X equals 1.4 and X equals 5.3 and for any X greater than 9.9. The intercepts of the graph are at the x-axis at negative 0.50 and 12.0, and the y-axis at 0 to 20. The relative minimum is 5.3133, and the relative maximum are 1.5 448 and 9.9 643. So there's two relative maximums. The end behavior, as X increases or decreases, the value of Y decreases. So from this, I'm guessing that our graph is probably going to be one of these guys. But we'll see. That's my guess right now. Another method for sketching a graph given key features is to first graph any given points. Then analyze intervals that have the same combinations of key features to make graphing easier. So let's start with our intercepts. We know the graph intersects the x-axis at negative 0.50 and 12.0. So we have a point here and a point here. And intersects the y-axis at 0 to 20. So we have a point there. The x-intercept means that the number of people in line is 0 at half an hour before the ride opens, and again at 12 hours after it opens. The y-intercept means that 220 people were in line when the ride opened. These points can be graphed on a coordinate plane. Right? So we're a half hour before we open, there's no one in line. Then the ride opens, we have 220 people, and then I don't know what happens in between, but we know that there is 0 right there. Again, 12 hours after we open. The graph intersects the x-axis at these 2 points. We already said that. This means that the ride experienced a relative low in the number of people in line 5.3 hours after the ride opened of about 133 people. That doesn't go with this right here, but that's okay. They did tell us above that at 5.3 hours, there was only 133 people in line. So we know that we dipped down right here. They also told us that at 1.4 hours, there were 448 people in line. So at 1.4, 448, we have a dot. And at 9.9 hours after the ride opened, there were 643 people. So at 9.9, we have a dot for 643. And these points can also be graphed. So now we can start to see the shape of our graph coming together. It's negative for anything less than negative 0.5, and it's increasing for anything less than 1.4, right? So we're going up to negative 0.5, and we're still increasing all the way up to 1.4. This indicates the number of people in line was negative, but increasing until a half hour before the ride opened. We also know that we're increasing at 5.3 to 9.9. Again, we're negative after everybody leaves and is no longer in line, and we're decreasing, so we're going down. And we're also decreasing from 1.4 to 5.3, and then all of this after 9.9 is decreasing. So it almost looks like a roller coaster itself, going up, coming back down, going back up, and coming back down. The end behavior, it's going to keep going down because no one's in line anymore. And the graph indicates a period where there is a negative number of people in line and more negative number of people in line a half hour before the ride opened and after the ride had been open for 12 hours. That word more is not needed. Since it's not possible to have a negative number of people, the graph appears to only model the number of people in line for the ride from a half hour before the ride opened until 12 hours after it opened. Meaning, in the context of the problem, we actually wouldn't even use these two sections here and here because we're not going to have a negative number of people.